all of these you should be familiar with the exception of maybe one. But you should have seen these at some point throughout your science classes. So units of measurement, as we talked about last class, every number needs a unit. Units are like clothing for our numbers. All right, we will never have naked numbers. You all don't run around naked. So your numbers are not going to run around naked. They always have to have a unit with them. Lets you know what you're measuring. So you have a little table, and you have a spot to write the name of how it's measured and your abbreviation. You do not have a space for the definition, because how many of you need to know the definition of mass? No one, all right? So, mass, is it the same as weight?
Kind of.
Kind of.
No.
What's the difference? Weight includes?
Object.
Pounds. Do you weigh the same? It's weight. It can be measured in pounds. Do you weigh the same on Earth as you would on the moon?
Yes.
Gravity. Mass never changes.
Gravity. All right. Weight is impacted by gravity, but mass. Does mass ever change?
Never.
No. So to find weight, it is your mass times by your gravity. So mass is basically a part of your weight. You take away all of the gravity around you.
Wait, so obviously you're going to learn less because of gravity, but you're going to technically use the same weight that you would be on.
You will have the same.
Except it's not going to look like it. It's not going to.
So if you weighed 96 grams, which you don't because that's really small, all right, whether you were on the moon or Earth,
You're still going to be 96 grams.
you're still going to weigh 96 grams. But if you're on Earth, 96 times 9.8, which is gravity. If you're on the moon, your weight would be 96 times 2.24 or something. So that's why your weight is different. Mass, weight, all right? Grams, pounds or newtons, all right? This setup will give you newtons. All right, so make sense the difference in mass? Only way mass would change is if you lost an arm or leg or a toe while you're flying to the moon.
So if you divided your weight by 9.8, would you get your mass?
If you had your weight in newtons, yes. Newtons is another measurement for,
Or does it by weight?
yeah, for weight. All right, so when we look at length, measured in meters, you all may be familiar with inches, but as you get into the sciences, you all became more familiar with meters, centimeters, things like that. Abbreviated with an M. All right, nice factors of 10 in order to measure meters and to convert between your different metric conversion prefixes. All right, and then you have time. We all know what time is. Sometimes it goes slowly, sometimes it feels like it goes fast. All right, measured in seconds, abbreviated with an S. If you ever do see it in minutes or hours, you would need to convert to seconds. How many seconds are in a minute? 60. How many minutes are in an hour? 60. All right, so be able to do that conversion, and so we'll look at those when we do some. Temperature. Notice the definition here of temperature might not be what you think it is. How much the molecules of a substance are what? Moving. Temperature measures the movement of particles. Not really how hot or cold it is. That's heat. All right. So we have two different ways of measuring it. You all may be familiar with Celsius. How do we measure it here in America?
Fahrenheit.
Fahrenheit. And most everywhere else is going to use Celsius. All right. Then we also have Kelvin. Has anybody heard of Kelvin before? One of you? Awesome. All right, so Kelvin is a way of measuring temperature that you never have a negative number. All right? So if temperature is how much the particles are moving, if I reach 0 Kelvin, what does that mean? They're no longer moving. They're not even vibrating. There's not the slightest movement occurring. All right? Can you get any more still than not moving? No, so you can't go negative here. Nothing, no life would exist at 0 Kelvin because nothing's moving, right? Even in a solid, particles are vibrating still.
What's the average temperature in Kelvin of what? Earth?
Of Earth, you would find the Celsius temperature of Earth and add 273 to it. Yep, so the conversion back and forth between Celsius and Kelvin is really easy. Celsius plus 273 gives you Kelvin. All right, so that means you can't ever get lower or colder than negative 273 Celsius.
So 273 is freezing.
Yes. Yep, because 0 degrees Celsius would be freezing, so 273 Kelvin. Good job. All right. Then we have amount of a substance. This is one you might not be very familiar with. We talked about it briefly the other day. We talked about our SI units. A dozen. All right, if I say I have a dozen, 1 dozen equals how much? All right, 12. So 1 mole equals 6.022 E, or times 10 to the 23rd. Oh, I wrote a 25. To the 20, my pen is lagging. To the 23rd. All right, so what that number is 6022. with 20 zeros behind it. That is 1 mole. So again, it's just showing you like 1 dozen is 12, 1 mole is this many. Somebody said, well, why in the world would I need to use that big of a number? Any ideas? Anything? What's the smallest thing though? Basis of all matter.
An atom.
An atom, yes. All right, so that helps us to measure the number of atoms that are present in a substance. So if I had a cup of water, I could weigh my water and based on the weight, determine the number of moles in that water and then find out how many exact little H2O molecules you had in that cup. All right, so that is our way of measuring the number of molecules because nobody wants to deal with this number, right? So, abbreviated with MOL, not an M because what does M stand for? Meters. All right, then we have volume. Everybody knows what the volume of something is, the amount of space that an object occupies. We all know that liters tells you how much you have to drink, right? Like you get a 2 liter. But for some reason, when we connect volume and liters, everybody forgets that those two things are the same. All right, volume is measured in liters. You may also see centimeters cubed. They're used interchangeably. There's no conversion between the two. Liters, centimeters cubed, both of them are going to tell you volume, amount of space an object occupies. Liters is mostly for liquids and gases. Centimeters cubed would be for your solids for the most part. For instance, if you had like a box or cube, length times width times height, centimeters cubed. All right, and then you have pressure. We're going to look at this when we get into gas laws. But I want you to go ahead and get familiar with these units. I didn't write out their full names because there's no need for you to write out atmospheric pressures, pounds per square inch, kilopascals. All right, but those are all different ways of measuring pressure. ATM, other than automatic teller machine, what does ATM stand for? Anybody know? Other than shorthand texting. Any ideas? I just said it.
Atmospheric pressure.
Atmospheric pressure. So where do you think that might be used?
Sky with weather and stuff.
In space, in the weather, yes. So if you get a barometer and it'll read the change in atmospheric pressure. So some people who get headaches based on if there's a lot of atmospheric pressure or low atmospheric pressure when it changes, that's measured in ATMs. PSIs. Any ideas?
Pressure per square.
Pounds per square inch.
Pounds per square inch. All right. What's measured in PSIs?
Like pressure of tires and stuff.
Pressure of tires. Good job, guys. Pressure in your tire. So if you open your driver's side door, you'll see a little chart, and it'll tell you what pressure per square inch your tires should be at, or pounds per square inch your tires should be at. Then you have torrs. That's another one used by meteorologists, and kilopascals is another way of measuring pressure as well. You won't see those commonly in everyday life as much. All right. So then we have this wonderful table that shows us the way we can convert by factors of 10 between our units of measurement. So hopefully you all have at least seen kilo, heka, deca, base, deci, centi, milli before, right? Math class, hopefully. So go ahead and fill those out in your table. Got your little mnemonic. King Henry died by drinking chocolate milk. Helps you remember the first letter of each of those. First Block the other day came up with one to add mega and micro. Micro, some of you are going to ask me what that is. That is a U with a fancy little tail. It's a Greek letter that we use to abbreviate micro. Because look, we already have a little M for milli and a big M for mega. Can't use another M here, so we have our Greek letter. All right, so we changed our mnemonic to add Mr. King Henry died by drinking chocolate milk, and then that looks like a U, so upside down. I don't know what First Block's fascination with drinking upside down is, but Mr. King Henry died by drinking chocolate milk.
Under the
upside
stairs.
down. Under the stairs.
That's a good one.
Thank you.
There you go, under the stairs. However, is going to help you remember the order of these prefixes.
You have quiz on all this?
You have a test on all of this.
You don't have a quiz first?
You should not need a quiz on just this introductory stuff.
What is the test?
Third and fourth. So yours will be the fourth.
So,
All right. So
That's next week.
For real?
it is next week. Can we stay focused on this?
I'm not
All right.
really
So notice these are called what? In yours it says, instead of just abbreviation, it says prefix. These are prefixes. So can I have a prefix by itself? Will you ever see capital M by itself?
sure. Never.
A prefix is not a word. It is added to the start of a word. So if I just had a lowercase m by itself, that would be a what? What's measured with a lowercase m?
Meters.
Meters. All right? So you will never see these by themselves, but that's one that tends to confuse people because they see a lowercase m all by itself and they're like milli. All right? Milli is not a unit of measurement. It's a prefix. All right? To make that number a little bit more manageable. Questions so far? So let's look at doing some conversions with these. Here are your prefixes. I will get used to remembering these. Mega, kilo, heka, deca, base, deci, centi, milli, micro. All right, so on your test, when you get to this, I would suggest writing down your M. Mr. King Henry died by drinking. These are lowercase, guys. Died by drinking chocolate milk under the stairs or upside down, whatever you want to remember. All right, what do you notice is between my milli and micro?
Three.
Three. How many are in between all the rest?
One.
Except the beginning.
One. All right? Yeah, so my two ends are threes. Everything else in between is one.
More zeros.
Yeah.
Where do you see zeros?
The zeros and the numbers.
So like
How
milli is
Oh, how many?
1,000,
Yes.
and then that goes
How many are in 1 gram? So notice 1 gram is smaller than a mega, so that's why it's 0.000. All right, let's look at why these are 3 away. All right, so if I was converting from grams to decigrams, I'd move my decimal 1 time to the right because it goes from 1 to 10 to the negative 1. All right, then negative 2, so 1 more jump. Negative 3, 1 more jump. But then this one says what? Negative, look at your paper.
Oh, it has 3 other lines because you add like 3 places.
It's 3 places. That one's 6. So instead of going 1, 2, 3, now it jumps to 6. So 1, 2, 3, and I'm at micrograms. Maybe say why? That's because by the time you get that small, all right, there's very few things that are going to be that small. We don't need a prefix for each of these things in between because it wouldn't be used enough, right? So instead of having 13 prefixes to remember, we're going to jump those spaces and we're going to category everything that small into our micro. Everything that's jumps past kilo is mega, giga, tera, and so forth, and it jumps by 3s because there's so few things that big, we don't need one to break up every single jump. All right, so over here, if I'm going to the left and I'm getting bigger, 1 jump, 2 jump, 3 jump, and now how many goes right here? 3, 4, 5, 6. All right, so when you're doing this, make sure you've got times 3 on each end. So this will be one of those good things that as soon as you get your paper, you write it down. This is going to follow you throughout the semester. All right? If you have your laptops out, when you're on your laptop, there is not anything that is on your laptop for this. It's up here. If you need the notes, you can go back to them later. All right, so let's look at some examples. How many milliliters are in 3.56 liters? So I'm starting where? What did they give me?
Your base.
They gave me liters. They gave me base. Do I see a prefix before it? No. So it's my base. And I want to go where? To milliliters. All right? So I'm starting at base, and I'm going to milliliters. Which way am I going to move the decimal? To the right. 1, 2, 3. When you draw your jumps, all right, you need to land on the prefix. Do not land on your dashes. 1, 2, 3 times to the right. So that 3.56 liters is 1, 2, 3. Oh, I have an empty seat. What do I put there? 0 is 3,560 milliliters. That's it. Yes, but a lot of people will get stumped by this as we keep going. So this is something to remember. It's easy. Remember it. Take it with you. Let's look at the next one. How many centimeters are in 12 meters? Is there a prefix here?
No.
Meters. So no, where am I starting?
Base.
Always start at what they give you. What they give you starts with a 12, right? They gave me meters. They did not give me centimeters. So now I want to find centi. Which way am I going?
To the right.
To the right. 1, 2. All right, so I had 12. There's no decimal there. Where's it at?
The
At the end.
1,200.
So, yep, good job.
Thank
1,
you.
2, fill it with zeros. 1,200 centimeters. All right, what is a comma? A placeholder. All right? Do not worry about your commas when you're moving decimals. The comma is not what you are moving. All right? You're only moving the decimal. All right? So don't let those commas confuse you. It's just a placeholder so that you can quickly see if you're in the thousandths, the millionths, and so forth. All right, and then the last one on your example. How many grams are in 0.056 megagrams?
Give megas.
I'm starting at mega. Yes, great job. Starting at mega, and I'm going where? To base. How many do I need to do to get to kilo?
3.
3. So 1, 2, 3, 4, 5, 6. All right, so instead of 0.56 megagrams, I have 1, 2, 3, 4, 5, 6. So I have 560,000 grams in a megagram. If you were working with this, would you rather deal with the number 560,000 or would you rather deal with 0.56? Some of you might like the whole number instead of the decimal. But this makes it a lot easier to deal with and record, right? Than keep writing out 6 numbers all the way across. Right? So that is where those prefixes help you. As well as if you're measuring in centimeters and you need to know meters for your equation, you can convert. All right, let's do one of the examples on the bottom because not all of them are going to go to the right. So let's look at one going to the left.
Is that 7 or 1?
Let's look at the middle one. That's a 17. But let's all look at the middle one together. All right, it says 40 point what? 40.64 microliters to what?
Meters.
Does it say micrometers?
Yeah.
All right, micrometers to meters. What is the lowercase m? Why is that not milli? It's not a prefix. All right? If it is by itself, that is always the base. All right? This is base. All right, so we know that micro, if I were to look, Mr. King Henry died by, there's my base, drinking chocolate milk upside down. And right here is a 3 difference. All right? So I have micrometers. 1, 2, 3, 4, 5, 6. Which way am I moving this time? To the left. So 1, 2, 3, 4, 5, 6. Fill in each seat. So you should have 4 zeros in front of that now. That's how many meters you have. So do the next 2 examples. The next 2 examples in your notes. The number that got cut off by the hole punch is a 17. So it's 17,000. That is a comma. Again, do we move commas? No. Good job, Ray.
Reach.
All right, so you should have ended up with 17.34, and then you should have 340, and then you should have ended up with what for your third one?
58.7 meters.
58.7. Good job. 17.340. All right, any questions on that? Awesome. So, let's move to SigFigs. This is the last part we're going to talk about today. SigFigs. How many of you are familiar with significant figures? Somebody say me.
No.
All right. SigFigs. So what are significant figures? If I tell you something significant, what does that mean? It's important. It matters. All right? If it's significant, most likely you know that to be a fact, and that's why it's so important. So, please, again, use your time wisely. You don't have to write word for word. I will bold the very important part and then paraphrase this to put it together for yourself, all right? Go ahead and practice those note-taking skills for college. So numbers in a quantitative measurement. Quantitative means what? Numbers or qualities? Quantitative. Replace that with a Y. What do you have? Quantity. So numbers. So numbers in a measurement and or calculations that are certain. You know for a fact that's what the number is. It wasn't your estimated number. Plus that one uncertain number. So when we've made measurements, if our tick marks gave us the tens, the ones, and the tenths place, we would have made one more estimate for the 100th place, right? So that's what it means by your uncertain number. Does everybody understand what it means by the 2 certain, 1 uncertain? All right? Or certain, it could be any number of certain, whatever your tick marks or calculations are going to give you. So let's look at when we're going to use them. Laboratory measurements. If you are in a lab and you measure something to say 17.64, and your partner says it was 18, right? And you're comparing your 2 recordings and you put them together, can you be any more precise than your partner who just decided to round off to the 1, please? No, right? Because now there's such an estimate that yours has lost its precision when you combine them together. So laboratory measurements, it's important to always go and use your SigFigs. All right, the least amount of SigFigs is the most specific you can be. Precise calculations, if you're calculating something your answer can't be more precise than your least precise part of your problem. All right, so abbreviate this here because you have a sheet that's going to help you out with this. But look for a decimal. Now we're going to determine how many SigFigs are present in a number. What you should write is present equals Pacific, which equals left. If the decimal is absent, it equals Atlantic, which equals right. Because Pacific and Atlantic are just a reminder key for you to know where to start. If it is present, you start at the Pacific Ocean. Well, which side of the U.S. is the Pacific Ocean on? The left. All right, if it's absent, there's the absence of a decimal. It's not there. Start at the Atlantic Ocean. It's on what side? On the right. We're going to look at some examples. So the first non-zero digit and each number you pass thereafter. We're going to look at some examples. Some of you may be like, what in the world are we talking about? All right. So flip to the next page. So here's where I told you didn't have to write all that because it's on your sheet for you. I gave you this nice little PDF there that says Pacific Ocean. It's going to explain what it means if your decimal is present. All right, so starting from the left side of the number, we're going to look for the first non-zero number. Let's look at an number example. They give us 0.00010 as our example. Is there a presence or an absence of a decimal? Present. All right, so since our decimal is present, it tells us to start from the left side of the number. All right, I'm on the left side. Imagine these are huge life-size numbers. You know, you see it like events and stuff, and they're life-size numbers. All right, and we're walking past it, and you are blindfolded. You cannot see anything until you reach the first non-zero number. All right, so I'm walking past it. Where do I get to take the blindfold off? At 1. All right, now I can see everything moving forward. You can't look back. You can see everything moving forward, and all of that counts. All right, you were blind. Now you can see. All right, once you hit that 1. So how many SigFigs do I have here? 2. 2 significant digits. Does that mean these zeros don't need to be there?
No.
If I were to say, oh, well, that means those zeros aren't significant, so I can just put 0.10. Is that the same?
No.
No. All right? These are placeholders. They are important. They are just not significant measurements. So what this is telling you is if you had a ruler, all right, and way out here is 0.1. All right? You're still like way down here. And say it's measuring to the tens, hundreds, thousands, 10,000s, 100,000s. Little bitty tick mark. So it's teeny, teeny, tiny. It has not even reached the 0.01 or the 0.001 yet. Right? This one has. So you are in those little tick marks. So that's what those zeros hold that place for, to say you're not here yet. You're still right here. All right? If I were to get rid of them, it says my object's big enough to get down here to 0.1. So that is why those zeros are important. It holds your place and lets you know. All right, let's look at Atlantic. Atlantic means what? Presence or absence? The absence of a decimal. So let's look at the number example that's in there. The example is 721,000. All right? So when we look at this, we said it's absent, so we're going to start from the Atlantic Ocean, which is on the right. I'm blindfolded until I hit a number that is not 0.
1.
Yes, good job. And then I can see everything. All right? So, how many SigFigs?
3.
3. All right, 3 SigFigs.
How do you ask this question on a head? Like, is it going to be like that?
Yeah, so I would give you a number, and I would say 860. How many SigFigs?
2.
Yes, I would say 0.02100. How many SigFigs?
4.
4. Why is it not 2?
Because
Because you're going from the left.
Said so.
Yes, going from the left, and I take my blindfold off, I can see everything once I pass it.
alright, wait. But on that, doesn't the zeros technically go on forever?
33.
Yes, but they could be estimated. So say you cut this off. This could be a full number. You could have rounded to 5 decimal places, and it could have been 2100163. And if I said round to 5 decimal places, right? So you don't know. There's so much uncertainty. If this was rounded up, say it was 0.0.
3.
Trying to think of a way. 20995, and I told you to round it to 5 decimal places. What does that 5 do to the 9? It rounds it up. So then you would have 0.02100. Same number, but look how this last number is an estimate. That's what got rounded as a result of what follows it. All right? That is not y'all's bell. I think that's the old bell because the other bell rang for spot.
Are you sure?
11:35.
Yeah, because
It's 11 right now.
rang like 4 times today.
Yeah. So they just haven't switched the bell schedule. All right. So does that make sense as to why that last 0? It's like you said. If you were punching in your calculator, you imagine it goes on and on and on. Questions here. All right. So let's go to your examples in the table at the bottom. Yes, in your notes. So flip back, back from the PDF, in this table.
Okay.
Yes. This table,
We have math problems on the test too.
yes. But it's basic addition, subtraction, multiplication, dividing. Yes. If you need a calculator to add and subtract, you can get it. All right. You will need one for this class, by the way, so if you don't have one, you should be working on getting one. No, but I would make sure you just have an E button on it, the exponent button. All right? So number, let's look at 200. Presence or absence? Absent. So I start at the Atlantic Ocean on the right. I'm blindfolded. I'm walking. Where do I finally get to see at?
2.
2. All right? So how many SigFigs? 1. All right? Presence or absence? Presence. All right? So I start at the Pacific Ocean. I'm blindfolded until I reach the 2. The first number I come to is a non-zero, and everything after that I can see. So how many SigFigs? 3. What number is this?
200.
What number is this?
No. 200.
200. Why is one of them 1 SigFig and one of them 3 SigFigs?
Decimal point starts on the left.
Yes, the decimal point. Good job. So let's look at
Age respects game.
some of you who may be wondering why. Trying to extend the page. All right. It's not going to give me a spot to write. So imagine we have a big beaker. All right. Beakers are for what? Are they for precise measurements?
No, that's the old stuff.
Just to hold stuff. So I've got 100. I've got 200. And I've got 300. They're for just estimates, right?
Yeah.
And if it's filled up to right here at 100, all right, and you say it falls right on that line, what is the only thing we can agree that says?
100.
100. That 00, somebody else might say, oh, I think it's 110. Somebody else might say, oh, no, I think it's 90. All right? So the only thing that I can estimate is this place, right? The next one has to be a 0, right? Your estimate would have been your 10 because all it gives you is the 100. So if I look at this, all of those are estimates. If I were to look at a graduated cylinder, and it had everything marked on it, It was like 100, 90, 80, 70, and so forth. And my water line falls at 100. All right? Somebody might think it says 99, but we're going to look at it like it falls right on 100. So I say 100. It's definitely not 110 or 190. It's definitely not 101. So I can say, okay, and we have tick marks here so that we can see those 10 tick marks. I know that it's not below. And so my estimate is at 0. Is it 99? Is it 101?
Wait,
Is
so
it 0?
when you're reading it for like a test and it's like what you see, you just write 100, right? You just write what you see.
Yes, but hold on. I'm showing you the difference in that decimal. So this one, all you know is that it's 100. You don't know these two numbers. Those are estimates, right? Over here, you know that it's 100. You know that it's not 90 or 110. So your estimate is this number, right? Because you have a tick mark for the hundreds place. You have tick marks for the tens place. So then you would have your period that says, I know this is 100. All right? No period says, okay, it's somewhere around 100, give or take a few. 100 period. I am certain. If you look at this, are you certain it's 100? If we look at a graduated cylinder, are we certain this is 100? No. All right, so like when you're talking to your friends and you're telling them something and you're like, period. This is it, right? You're saying, okay, like, I don't know, I'm fed up with this, period. What does that mean?
You're not.
No.
You know it, right? You're certain. You're like definite. So when you put that period there, it's like definite. All right, I know this is 100, no question about it.
Boom.
No period, you don't know. So that's why 200 versus 200 is different. Does that make sense? All right. Which most of you seem to get that when we did it. But for those of you who were maybe still questioning the difference.
Why is it really big?
Hold on, what?
Why is it like messed up?
I don't know. It's moving slow for some reason. All right. 3890. Present. So I start at the Pacific, which is on the left coast, right?
Yeah.
So I put my blindfold on, and as soon as I start my number, I get to start counting. As soon as I'm walking this way
Oh.
from the Pacific Ocean. All right. On this one, I walk this way. On this one, I walk that way. All right. So I start walking, and as soon as I get to my number, do I get to take my blindfold off?
Yeah.
Yes. Remember, we can
Stop
see
at 8,
everything in front of us.
right?
I can see everything in front of me now. Once you take it off, I was blind, now I can see. Do you want to go back blind again? No, so you can see everything. So 3890, you see all of it. So how many?
4.
4. Imagine them as like, have you ever been to like conferences and they have
Wait.
the huge life-size numbers and you like take pictures beside the numbers? Yes, no, anybody? Like anybody's birthday party have the huge numbers, cardboard numbers? All right, imagine that's what you're walking past. Would you still see that 0 now that you took your blindfold off? Yeah, so that's why we get to count it.
So like when you take, so like, since it's 3.890, like there's no steps, so you can look behind and in front of you.
What would I be looking behind to?
The 3, right?
No, because I took it off at the 3. I can see where I'm at and
So
everything
does it
beyond.
start where the decimal is, it starts from the beginning of the number?
No, the only thing the decimal tells me is whether or not I have a decimal present or a decimal absent.
Oh.
That's the only thing I'm looking at that decimal
I
for.
was confused. I thought it started at the decimal.
No, good question. Yeah, the examples we did a second ago, they did start, it was set up that way to where it fit what you were thinking. But no, it's the only thing the decimal matters is whether or not it's there or not. All right, so let's look at the next one. Presents or absent? Present. So I start on the left side. I'm coming from this side. I'm walking past it. Where do I get to take my blindfold off at? 6, and I can see everything beyond that. So there's 3 of them. Yes. Good job. Absence or presence? All right, so I start at the Atlantic Ocean. I get to take my blindfold off when I reach the
5.
5.
3.
So there's 3. Yes. Great job, guys. Presence or absence?
Presents.
Present. All right. Starting at the Pacific Ocean.
See a lot of numbers.
Yes, a lot of numbers.
1, 2, 3, 4, 5, 6, 7, 8.
1, 2, 3, 4, 5, 6, 7, 8, 9. Yes.
Wait, why?
Because there's a 6 in the beginning.
6. I took my blindfold off at 6. Do you want to go back blind again?
No.
No. So you can see everything in front of you
Then
now.
why is the fourth one not 6?
Right here?
Oh, never mind. I get it.
Because it's not until
I
you
got it,
reach
I got
a
it.
non-zero number. Yep. All right, the last one.
That's multiplication.
That's a good one.
Thanks.
It is, but what is this called?
A numerator.
No, it's called like thousands.
No.
You just add 8 zeros.
The type of notation.
Like
You
scientific.
add zeros. Yes, scientific.
Scientific.
Yes, good job. So this right here
Numerator.
tells you how many times your decimal's been moved. All right? So first let's look at how to count the SigFigs, and then we'll talk about why.
Oh, the board.
It's a bit laggy today. I've had more. So we'll fix your internet.
Jack.
Jack, stop.
All right. So 7.35 is what we're going to focus on. Shh. When you all see scientific notation, all you're worried about is this number. We don't care about the times 10 to the 8th. Shh. All right. So how many do I have? Yes,
3.
presence of a decimal. Start at the Pacific. Everything I get to count as soon as I hit that non-zero digit. So 3.
So just mark out the
Yes, I'm going to show you why you don't worry about that. All right? 735 times 10 to the 8th is like saying 735. Once I move my decimal 8 times to the right. All right? So say you get a number in the lab and you get 735, 2, 5, 8, 9, 1. All right? And then say you get 7, 3, 4, 8, 5, 8, 2, 6. All right? If I put each of those numbers in scientific notation, that means how many numbers in front of my decimal? Only 1. So by the time I move this forward 8 times, I don't know if I counted my loops right, but 8 times, this one would be what? 7.35
0, 0, 0, 0, 0. Oh.
times 10 to the
8.
8. This next one, if I put it in scientific notation, is also going to be what?
7 point.
What is this 2? If I cut it off here, this 2, do I need to round up my 5?
No.
No, so 7.35 times 10 to the
8.
8. Look at the next number. Moving it forward.
7.34.
You need another number. So
7.3.
7.3, wait a minute, 7.3,
Oh.
this 8 makes my 4 round up to a
5.
5.
Times 10 to the 8.
So, look at that. Those are all 3 different numbers, right?
But they're all in
I would much rather have this bank account than one of these two. Makes a significant difference, right?
Yeah.
So, why do we not count all of these zeros? Because I don't know what they are, right? I don't know if they're actually zeros or if they're all these different numbers and different possibilities. So that's why we don't worry about this. This is all an estimate. It's all been rounded off. All of it is not exact. Here, again, these 2 numbers are estimates. It's all based on what follows it, whether or not it got rounded up or not. So that's why we only care about your 7.35. Questions? All right, so let's look at addition and subtraction. These are 2 really quick rules with addition and subtraction, and then multiply and divide. Flip your page twice. All right, you can shorten this down if you want. This is only points. There's just a lot of room there. All right, normal math. Do your math like normal. right? And then round to the least number of decimal places. Please write decimal places really big because that is what matters. Number of decimal places. This is what makes the difference between addition and subtraction and multiply and divide. Least number of decimal places.
Go
Yes.
to the bathroom.
And that's a.
Oh.
All right. So, round to the least number of decimal places. Let's look at some examples. You have 3 to go across the top there. 28.0 and 16. Plus.
Oh, plus it's not
44. So what did your rule tell you? The least number of
Decimal point 0.
decimal places present in those two numbers. So if we're comparing them, you had a really exact measurement in the lab, and your partner was like, nah, I'm just going to round it. What did I tell you about your answer?
that part.
It's less accurate. You can no longer be as specific as you were. All right, all that hard work went to waste. You're now stuck with a really rounded up answer. All right, so if we look at this, this has 1 decimal place. This has how many decimal places? 0. So my answer has to have how many decimal places?
0.
0. Yes. Least amount of decimal places.
So don't worry about that 0 at the
Correct. You're rounding it.
Wait, so no 0.
No 0. You can mark it out. That way you can see that you crossed it out. So like I said, do your math as normal, and then you cut it off after you round it. All right? 28 plus 16, that still gives you 44. But both of these have how many decimal places? 2. So can my answer have 2 decimal places? Yes. And then 28 plus 16, my answer has no decimal places. Neither does my problem. Either number is in my problem. So do I need any decimals?
No.
No. Always go by whichever one shows the least. Do the 3 at the bottom. Is it an emergency?
No.
Okay. For the next.
Kind of.
So at the bottom, your first one should have had how many decimals?
2.
2. Your next one?
0.
And the next one?
0.
Great job.
This is easy.
I am very glad you all keep still. That's awesome.
Oh, multiply.
On the load.
Multiply and division. Again, math is normal. Multiply and divide just like you always would. This one is based on the least number of total SigFigs. Make that big. Add and subtract was based on what? Decimal places. Alright, so plus, minus, based on decimal places. Multiply and divide are based on what? Total SigFigs. Total significant figures. So have you ever heard the term, you can't be stronger than your weakest link? Yes? Alright? If you are running a race and it's dependent on everybody finishing, whose time counts?
Everybody.
The last person, right? Whoever's the slowest. So same thing here with our numbers. You cannot be more specific than your least specific answer. Your answer can't be any stronger than your weakest answer. You can't finish more precise than the least precise measurement. All right? So based on the total number of SigFigs. So let's look at the first one. 24 times 2 is 48. Follow our math rules. We have 48.0, right? But how many SigFigs are in both of those?
1. We needed 0. Oh, no.
Met.
Wrong problem.
Not present, but both of those are numbers greater than 0.
Ours has
Go to the second row.
Oh.
Second row. Sorry, guys. Second row. 48. 2 SigFigs and 24, right? 2.0. Decimals present. Start at the Pacific. I get to take my blindfold off at the 2, and I can see everything that I pass going to the right after that. So how many is there? 2. So my answer can only have how many SigFigs? 2. Right now it has how many? 3. So I'm going to cut this off and round it off. Yep. Now, if that happened to be a 0.5, say it was 48.5, and I said I can only have 2 SigFigs.
49.
49.
Why only 2 SigFigs?
How many is in 24?
That's 2.
2. How many in 2.0?
1, 2.
2. Present. So we're walking to the right. Everything we pass after that 2. All right. So if I have this, that means I know that my measurement is the 0.0. Did this person measure the 0.0?
No.
No. So because of that, I can't have a 0.0 because I don't know the tens place anymore.
Yes, you gotta take 0 out.
Yes, so that's why we took the 0 out. Because your lab partner was lazy and didn't measure to the decimal point.
That's terrible part.
All right? Yes, find your new partner. Next one is divide. Go straight across this one beside it. All right? 24 divided by 2.
Whoa.
12. If we follow our math rules, we should have 2 decimal places there.
12.0. No, you gotta take the 0.
Let's look at it. 24, present, so going to the right. How many do I have? 2.0, present, so I'm going to the right. 2. Who has the fewest?
2.
2. So how many decimal places can I have? Can I have any? No, I've got to round it till there's 2 SigFigs.
Oh.
But that's, you gotta convert it too.
This would give you density. You're talking about convert it because their units are different?
Yeah.
Yeah, so this would give you density, which would be grams per milliliter. Good job noticing that.
Thanks.
Questions?